Hey everyone, have you ever stopped to think about a really cool chemistry puzzle that's happening literally all around us every single day? I mean, think about it. Why do fireworks just explode? You get this incredible, brilliant flash of light and sound, and then, boof, it's all over in just a few seconds. But then, on the other hand, you have something like an old iron nail. You leave it outside, and it takes forever. We're talking weeks, maybe even months, to slowly, painfully surrender to rust. So what gives? They're both chemical reactions, right? Why is one so fast and the other so incredibly slow?
Well, it all boils down to one key idea: the rate of a chemical reaction. And don't let the name scare you. It's really just a fancy way of saying how fast your starting ingredients, which chemists call reactants, turn into the final thing you're trying to make, the products.
And believe me, this speed is all over the map. You've got your lightning fast reactions like those fireworks. Then there are ones that take a few hours, like making soap from scratch. Others, like that poor rusty nail, take months. And then you get to the really epic ones, like petroleum forming deep in the earth. We're talking millions of years for that to happen. It's just a mind-boggling range of timescales.
So at its core, every reaction is kind of like a seesaw. When you start, on one side, you've got 100% of your initial stuff, the reactants. As time goes on, that side goes down as the reactants get used up, and the other side, the products, starts to rise, all the way up to 100%.
Okay, so here's the cool part. This speed isn't just some random thing we have to live with. Nope, we can actually control it. There are these levers we can pull to either hit the gas or pump the brakes on a reaction. So let's jump in and check out the 4 main ways we can get in the driver's seat.
All right, factor number 1, and this is a big one. It's just the nature of the stuff you're working with. Let's be real, not all chemicals are created equal. Some are just naturally more eager to react than others. And a huge part of that comes down to their chemical bonds. See, things with ionic bonds, think table salt, they just fall apart into these zippy little charged ions when you put them in water. And those ions are ready to party. They react super fast. But then you have covalent compounds. They're a bit more stubborn. They have to react as a whole molecule, which is way clunkier and, you guessed it, a lot slower.
And it's not just the bonds. The physical shape matters too. You've seen this, right? Try dissolving a sugar cube versus powdered sugar in your teep. The powder disappears in a flash. Why? More surface area. It's the exact same principle in chemistry. An acid trying to react with a big chunk of iron can only nibble at the outside. But if you grind that iron into a powder, whoa, now the acid can attack everywhere at once, and the reaction just takes off.
Okay, on to our second lever of control, and this one is super intuitive: concentration. Basically, it's just about how crowded the molecules are. The easiest way to think about this is like a crowded room at a party. If there are only 3 people in a huge hall, they might never bump into each other. But pack that same room with 300 people, collisions are going to happen, guaranteed. Well, molecules are the same way. The more you pack into a space, the higher the concentration, the more they're going to collide, and every collision is a chance for a reaction to happen.
And we can see this in action really clearly. If you drop a bit of magnesium into some weak dilute acid, you'll get some bubbles, sure, but it's pretty tame. Now, do the same thing with super concentrated acid. It goes crazy. Way more bubbles, way faster. Why? More acid molecules means more collisions per second. Simple as that. Let's move on to factor number 3, and this is one you already know from your own kitchen: temperature. We're talking heat. So, why does cranking up the heat make things go faster? It's all about energy. When you heat molecules up, you're basically giving them a shot of espresso. They get super energized and start zipping around like crazy. This does 2 things. 1, they bump into each other way more often. And 2, when they do collide, they hit with a lot more force. Both of those things mean you get more successful reaction-causing collisions. You can test this yourself with one of those fizzy effervescent tablets. Drop one in a glass of ice-cold water. It's a pretty slow, kind of lazy fizz, right? The molecules are sluggish. Now try it in a mug of hot water. Fizz, it goes wild. It's the same tablet, the same water. The only difference is the temperature. But look at that massive change in speed. All right, time for our last factor, and this one is like a secret weapon for chemists. It's called a catalyst. You can think of it like a chemical coach or a super efficient matchmaker. So what makes a catalyst so special? Well, its whole job is to speed up a reaction. But here's the really mind-blowing part. It doesn't get used up at all.
It just helps the other molecules react, and then it walks away completely unchanged, ready to go help the next pair. It's incredible.
So how does it work, this magic? Well, most reactions need a certain amount of energy to get started. Chemists call this activation energy. Think of it like trying to push a giant boulder over a really tall hill. It takes a ton of effort. What a catalyst does is basically build a shortcut, a tunnel straight through the hill. It provides an easier path so the reaction can happen with way less energy. And because of that, it happens way, way faster.
A classic lab experiment shows this perfectly. If you just leave a bottle of hydrogen peroxide sitting there, it will eventually break down into water and oxygen, but it would take ages. Now add just a pinch of a black powder called manganese dioxide, that's our catalyst, and bam, the reaction just explodes with activity. You get this massive rush of oxygen bubbles, all happening almost instantly. That's the power of a catalyst.
So there you have it, our 4 big levers of control. What this stuff is made of, how much of it there is, how hot it is, and whether you've got a catalyst. But why does any of this actually matter? Well, it turns out controlling the speed of chemistry is not just important, it's absolutely vital for pretty much everything.
I mean, look no further than your own body. Right this second, you have things called enzymes, which are just biological catalysts, making your digestion happen millions of times faster than it would otherwise. You literally wouldn't be alive without them. Or think about your car, that catalytic converter. It's packed with catalysts that turn nasty exhaust fumes into much safer stuff. Even something as simple as baking bread, that's yeast acting as a catalyst to make the dough rise. They are literally everywhere.
So yeah, those are the 4 big secrets to controlling the speed of chemistry. And that kind of leaves us with a fun question to think about. Now that you know how to pull the levers, think about your daily life. Is there a chemical reaction you wish you could speed up? Maybe make your food cook faster. And, maybe more interesting, is there one you'd want to slow way down? Maybe stop your bike from rusting. The power is all around you. Pretty cool to think about, right? Thanks for joining me.